Good morning, class. Today we are going to continue with our physics UTME class. All right, so we stopped in the last class at thermal expansivity where I explained linear expansivity in the last class. So if you missed the last class, you can just go over to the next class. So in the last class, go to YouTube and go to tpaths channel on YouTube and you'll be able to watch the video, be able to watch the class. Okay, so we stopped at thermal expansivity. So in the last class, I think we stopped at the working example. There was an example we were working on, but because of time, we couldn't continue. So I'm just going to go over the example again. All right. So the question says the brass measuring tape is correct at 20 degrees Celsius. The value obtained when the length of a field is measured with the rule at 50 degrees Celsius appears to be 70.5 meters. What is the true length of the field? If linear is brass is 1.6 times 10 square minus 5 per Kelvin. All right. So what I'm going to do is I'm just going to fit some parameters and go to interpret my question. So a brass measuring tape is correct at 20 degrees Celsius. In the last class I explained that I'm going to take that as my theta 1. So I move to the next one. The value obtained when the length of a field is measured with the meter rule at 50 degrees Celsius. So 50 degrees Celsius is my theta 2. Appears to be 70.5 meters. So now when a field was measured at 50 degrees Celsius, the length of that field was 70.5 meters. So which means that length that I just measured is the length at theta 2. So this is L2, 70.5 meters. You know, I said L2 is the length at theta 2, while L1 is the length at theta 1. So now I don't know what my L1 is. And that's what I'm asked to calculate in the question. So now the question says linear expansivity of brass is 1.8 times 10 to the power minus 5 factorial. So 1.8 times 10 to the power minus 5. So I have my linear expansivity. I have my final length, final temperature, initial temperature, and this is my initial length which I'm asked to look for. So now, first I want to find my theta. Theta is change in temperature, right? So theta is equal to theta 2 minus theta 1. So what's my theta 2? My theta 2 is 50 degrees Celsius, while my theta 1 is 20 degrees Celsius. So I'm just going to say theta is equal to 50 minus 20, 30 degrees Celsius. So my theta is 30 degrees Celsius. Don't forget, the formula for calculating linear expansivity is this linear expansivity equals to L2 minus L1 over L1 theta. So now what I'm going to do is I'm just going to replace all of these parameters into my formula here. So my linear expansivity, which is alpha, is 1.8 times 10 to the power minus 5, right? My L2 is 70.5 meter minus L1, which is the unknown that I'm looking for, then L1 times 30. Right? So I'm going to cross multiply here. That's this times this. So this is going to give me 5.4 times 10 to the power minus 4 L1 is equal to 70.5 minus L1. So now what I want to do here is I'm going to simply collect like terms. I have L1 here and I have L1 here. I'm simply going to collect like terms. So collecting like terms, I'm going to bring this L1 to this side. So the sign is going to change from negative to positive. All right. So I'm going to do that now. So first of all, what I have to do is I have to replace change this from standard form to the so this is 0.00054, right? 0.0054 is equal to 70.5. Okay, sorry, I have to put my L1 minus L1. So now I'm collecting like terms. I'll bring this to this side. So this will become L1 plus 4 L1 is equal to 70.5. Now this is going to give me 1.00054 L1 is equal to 70.5. So now for me to get the value of my L1, I'm simply going to divide through by 1.00054. So I'm going to divide by 1.0054. All right, so this is what I have. So if I'm dividing through, okay, I'll just continue at this side. So I will say L1 is equal to 70.5 divided by 1.00054. Then when I divide that, I have my L1 to be equal to 70.46 meters. So what I'll go to the question and then look for the option with 70.46 meters after dividing. So the value that corresponds with my answer here, or the option that corresponds with my answer here is option C, which is 70.56 meters. So 70.56 meters is the length of the field when measured with tape at 20 degrees Celsius. Why 70.5 meters is the length of that field when measured tape at 50 degrees Celsius. So this is my initial length that I was asked to find, 70.46 meters. I hope you guys are getting it. All right, we move to the next example. The next example says a metal rod has a length of 100 centimeters at 20 degrees Celsius. A metal rod has a length of 100 centimeters at 200 degrees Celsius. At what temperature will its length be 99.4 centimeters if the linear expansivity of the material of the rod is 2 times 10 to the power minus 5 per Celsius? All right. So what I'm going to do is I'm going to list out my parameters. First is my linear expansivity. It says 2 times 10 to the power minus 5 per Celsius. It can be per Celsius or per Kelvin. All right. So I have this. So this is the way I'm working on. So you guys should see it here. So, all right, I've written down my alpha. So the next thing, a metal rod has a length of 100 centimeters at 200 degrees Celsius. At what pressure will it be 4 centimeters? So here is at the length of 100 centimeters, its temperature is 200 degrees Celsius. So I'll say at L2, 100 centimeters, and then at theta 2, it is 200 degrees Celsius. But then at L1, it is 99.4 centimeters, and then theta 1 is what I don't know. All right. So the temperature at 99.4 centimeters is what they are asking us to find. The temperature at 100 centimeters is simply 200 degrees Celsius. Why this is by linear expansivity. All right. So what I want to do here is, firstly, I want to convert these centimeters to the standard unit, which is meter. So converting to meter, I'll just divide through by 100. All right. So dividing by 100, if I divide 100 by 100, I'll have 1 meter. So my L2 is 1 meter. And if I divide this by 100, I'll have 0.994 meter. All right. So now this is what I have. I have my L2 as 1 meter and my L1 as 0.994 meter. So what I'm going to do is I'm going to use my formula, which I'm going to just complete to the side. So I'm going to continue on this side. It says alpha equals L2 minus L1 over alpha theta 2, sorry, L1 theta 2 minus theta 1. All right. So what I'm going to do here is alpha L2 is 1 minus 0.994 over 0.994 times, what's my theta 2? My theta 2 is 200 minus theta 1, which is what I'm looking for, the ratio at L1. So my alpha is, which is linear expansivity, 2 times 10 to the power minus 5, is equal to 1. So 1 minus 0.994 is going to give me 0.006. I'm correct. Yes, 0.006 divided by 0.994 by 200 minus 1. So yeah, what I'm going to do is I'm going to cross multiply. All right, I'm going to cross multiply. So I'll have 2 times 10 to the power minus 5 times 0.994 open bracket 200 minus 1 equal to 0.006. So what I want to do here is I don't want to just, what I want to do is I don't want to open this bracket. So I'll just multiply this by this, divide through by this, then I can collect like terms. Are you with me? So I'll just divide this, I'll multiply this 2, then I'll divide through by this, then after that I can collect like terms. So I can make it easier. So I won't make things complex. All right, so multiplying this by 0.994, so 2 times, so this is going to give me 1.988 times 10 to the power minus 5 times 200 minus theta 1 equals to 0.006. So I have this. So what I'm going to do is I'm going to divide through by this. I'm going to divide through by 1.98 times 10 to the power minus 5. I hope you guys are following me. So dividing through, this is going to cancel out this. So I'll have 200 minus theta 1 will be equal to, let me divide that, 0.006 divided by 1.988 times 10 to the power minus 5. Okay, so this is giving me 301.8. 301.8 as my theta 1. sorry, after dividing it, 301.8. So what I'm going to do is I'm going to collect like terms. I'm going to bring this to the side and take this to the side. So I have 200 minus 30, sorry, theta 1 equal to 301.8 minus 200, which is going to give me 201.8 degree, 101, sorry, 101.8 degrees Celsius. So I'm going to check the option that corresponds with my answer here, 101.8 degrees Celsius. Or sorry, I made a mistake somewhere. This should be, when I'm bringing this to this side, this should be coming to this side, all right? So when this is coming to this side, this is going to this side. So it becomes 200 minus 301.8, not 301.8 minus 200. So this is coming to this side. So it's a sign of this that's changing. Why this is moving to this side equals to theta 1. So when I subtract this, I want to have theta 1 is equal to minus 101.8 degrees Celsius. So my theta 1 is minus 101.8 degrees Celsius. So if I check the option, the one that is closest to the answer is option D. Why? Because they converted it to the nearest hundreds. If I'm converting this to the nearest hundred, I have my theta 1 is equal to minus 100 degrees Celsius. It's the nearest hundreds. Use the approximation sign. It's the nearest hundreds. Or I can say to the nearest whole number. So that was just approximation. So my answer is minus 100 degrees Celsius, which is option D. All right. So what I just did is, when you have the question, you interpret it. After your interpretation, you fill in the parameters given in the question into your formula, and then you start solving step by step. You start where you have to multiply, you multiply. When you have to divide, you divide. Then after doing all of that, you just leave you have to find the answer, and then you check the option that corresponds with the answer. And then another thing you should have to be considering is speed. Speed is very paramount. All right, so that's linear expansivity. So now we'll be moving to area expansivity. So area expansivity is the change in area per unit area per degree rise in temperature. So it is the change in area per unit area per degree rise in temperature. In the last class, I explained linear expansivity, which is the change in length per unit length per degree rise in temperature. Now, area expansivity is simply change in area per unit area per degree rise in temperature. Another thing is area expansivity is sometimes called superficial expansivity. So you have that at the back of your mind. It might not be called area expansivity, it might be called superficial expansivity. All right. So it is the change in area per unit area per rise in temperature, and it is denoted by beta. So beta is like a B having a stroke, but it's a Greek alphabet. So area expansivity is denoted by beta, and then the formula is this. Formula is given as this. Beta is equal to A2 minus A1 over A1 theta 2 minus theta 1. Or you can say beta is equal to A2 minus A1 over A1 theta. All right. So here is the formula for calculating area expansivity, or superficial expansivity. So here is the beta I was talking about. This is beta. This is the denotation of this is the representation or denotation of area expansivity. So now I have A2. A2 is the area at the temperature 2. Why A1 is the area at temperature 1. Why A1 is my area. This is my area expansivity. Why theta is simply the change in temperature. Theta 2 minus theta 1. I can write it as this, or I write it as this, depending on how my question comes up. So these are the two formulas you can use. They are basically the same thing. You can use this or use this. They're the same thing. Okay. So I said area expansivity is the change in area. That's why I have A2 minus A1, which is area of a particular material per unit area, then per degree rise in temperature. All right. So now we'll move to relationship between area expansivity and linear expansivity. Relationship between area expansivity and linear expansivity. So at this point, I want you guys to be very, very attentive, because I'll be doing something very important here. All right. So here I have what you want to do is you want to get the relationship between area expansivity and linear expansivity. So this is my area expansivity. Why this is linear expansivity. Yes, you guys can see this. So linear expansivity, and here is area expansivity. So now what I want to do here is I want to find the relationship between these two. That's beta and alpha. So now first thing is I want to cross multiply for linear expansivity. And I have when I cross multiply, I'll have alpha L1 theta, right? Is equal to L2 minus L1. And I can also say L2 minus L1 is equal to alpha L1 theta. So now here I want to make L2 the subject of the formula, right? That means I want to make L1 theta and alpha in terms of L2. That's L2 will become L1. That's because this negative sign is coming here, it's become positive sign. That's why there's no negative sign here. Then plus alpha L1 theta. So here now I can make L1 common because L1 is common. I can bring L1 out. So this will become L2 equals to L1, 1 plus alpha theta. So I have this. Probably let me just call this equation one. But I don't think it's necessary. We just refer back to this equation one. So I have this for my linear expansivity. I got this from my linear expansivity. So if I do the same thing, definitely for my area expansivity, I'm going to cross multiply and then collect like terms. I should also have A2 equals to A1, open bracket 1 plus beta theta. I guess you guys are agreeing with me. Because if I do the same thing, I'll just cross multiply. After cross multiplying, I'll have A2 minus A1 is equal to beta A1 theta. So what I'm going to do is I'm going to make A2 the subject of formula like I did here, and then I'll have A1 plus beta A1 theta, and then I'm going to make A1 and I'm going to bring it out like this. So I'll have 1 plus beta theta. So now here, if I open the bracket back, I'm definitely going to get this back. And if I open the bracket back, I'm going to get this there. So all right, so I can just name these two. So now here I got this from linear expansivity and I got this from my area expansivity. So I have these two. Now, don't forget what I'm trying to look for is relationship between area expansivity and linear expansivity. So, right. If you remember when you were doing mensuration in secondary school mathematics, they said area is length times breadth, right? So which means area is equal to length times breadth. So now, which means I can say area 1 or A1 is equal to L1 times B1. Are you agreeing with me? And I can also say A2 is equal to L2 times B2, right? So this is this. I have A1, so my A1 become L1 B1, while my A2 become L2. So what I want to do here is I want to replace this L2B2 and this L1B1 for A1 in this equation 2. What do I mean? Where anywhere I'm seeing A2, I want to put L2B2. And anywhere I'm seeing A1, I want to put L1B1 in this equation 2. So how do I go about that? I'm simply going to write, instead of writing A2 here, I write L2B2. L2B2 is equal to, and instead of writing A1 here, I'm writing L1B1. I hope you guys are following me. So open bracket 1 plus beta theta. Don't forget, this is what I'm substituting into. I'm substituting into equation 2. I'm substituting the values of these two guys. That's A1 and then A2 into equation 2. So that's why I have this. Now, don't forget, when we come back to this place, we said L2 is equals to L1 plus alpha A1 theta, right? Sorry, L2 is equals to L1 open bracket 1 plus alpha theta, right? So which means L2 is equals to L1 open bracket 1 plus alpha theta. Then B2 will also be equal to B1 open bracket 1 plus alpha theta. So what I'm going to do again is here I'm going to substitute L1 open bracket 1 plus alpha theta and then B2 equals to for this guy in this equation. So I can name this equation 3. So I want to substitute these two values for L2 and B2 in this equation 3. So I'll put this in. So instead of having L2, I'm going to write L1 open bracket 1 plus alpha theta. Then times, instead of writing B2, I write this B1 open bracket 1 plus alpha theta. All right, is equal to L1 B1 open bracket 1 plus beta theta. I hope you guys are. So, all right, what I'm going to do here is I'm going to multiply these two guys, L1 B1 open bracket 1 plus alpha theta square. Right, alpha 1 plus alpha theta plus times 1 plus alpha theta will give 1 plus alpha theta square. So it's equal to L1 B1 open bracket 1 plus beta theta. So from here, L1 B1 is common, right? Which means they can cancel themselves out. This is going to cancel out this. So what I'm left with is 1 plus alpha theta square. So I'm just going to do it like this. It's equal to 1 plus beta theta. So what I want to do here is I want to open these brackets. I want to open these brackets. So I'm saying 1 times 1 is 1. 1 times this alpha theta alpha theta times 1, alpha theta, then alpha theta times alpha theta square. I hope you guys know how I do this. What I'm simply doing is 1 times 1, 1, 1 times alpha theta times 1, alpha theta, and alpha theta times alpha theta square equal to 1 plus beta theta. So right now, what I'm going to do here is I'm going to collect like things. 1 plus 2 alpha theta. That's alpha theta plus alpha theta give me 2 alpha theta plus alpha square theta square equals 1 plus beta theta. So here, in this case or scenario, when you have linear expansivity, the value of most linear expansivity is also always a number raised to the power of -4. Like you can have the linear expansivity 1.8 times 10 to the power of -5, or you have the linear expansivity of the material as 2 times 10 to the power of -5. So now if you are squaring this, the value of this is very, very negligible. So this is going to give me 2 times 10 to the power of -10, which is going to give me so many things, 0.2. That's if I square this, I'm going to have this. So, okay, sorry, 4. So if I square this is going to give me this. That's the square of alpha is going to give me this. And if I square this, it's going to give me so many number of zeros that I can just neglect them. So which means alpha square is very, very negligible. Or you can say it's equal to 0. So when you see alpha square or alpha cube or something, you can take it as 0. So which means I'm going to take my alpha square here as 0 because the value of alpha square is very negligible. So this is going to become 1 plus 2 alpha theta plus alpha square is negligible. So it's going to become 0 times theta square equals 1 plus beta theta. All right, so this is going to become 1 plus 2 alpha theta. So anything multiplied by 0 is 0. It's equal to 1 plus beta theta. Okay, what I'm to do here is, all right. Simply going to continue from here. So I'll continue this from here. I have 1 plus 2 alpha theta is equal to 1 plus beta theta. So here I can subtract 1 from here, and then I'll have beta theta is equal to 2 alpha theta. So theta is common, right? So theta can cancel out theta, and then I have beta is equal to 2 alpha. So now the relationship between linear expansivity and area expansivity is this. So this is what we've been trying to do since beta is equals to 2 alpha. So this is like a proof of beta is equals to 2 alpha. So now the relationship between this area expansivity and linear expansivity is beta is equals to 2 alpha. Okay, let me go over it just quick. So this is what we have. I have this as my area expansivity. I have this as my linear expansivity. What I simply did is this linear expansivity, I made L to the subject of formula, that is length 2 or final length, and then I got this. How did I do that? I first cross multiplied, I got this, then making L to the subject of formula, I bring this to this, and then I bring L1 out of the bracket, and I have this. So if I do the same thing for my area expansivity also, I'm going to have this. So now from here, I said, don't forget, area is equals to length times breadth. So if area A is equals to length times breadth, A1 will be equals to L1 times B1, and then A2 will be equals to L2 times B2, right? All right, so this is what we have. So now moving ahead, I'm saying I have L2 times, I simply said I wanted to substitute these values for in equation 2. Anywhere I see A2, I'll put L2B2, which is the value of A2 here. And anywhere I see A1, I'm going to put L1B1. So I'm substituting L1 for P1. I'm substituting L1B1 for A1 in equation 2 and L2B2 for A2 in this equation 2. So that's what I'm doing. So doing this, I continued and I also said L2 is equals to L1 this, and I said B2 is also equals to this. So I substituted everything, and I have this L1B1 can cancel out L1B1, and then I open this bracket, I add this, and don't forget I said alpha square, which is linear expansivity, the square of linear expansivity is very negligible. Just to have so many zeros, so it's very negligible. So I took it as 0, and then 0, anything multiplied by 0 is 0, and then I have this 1 plus 2 alpha equals to alpha theta, and at the end of the day, came up beta equals to 2 alpha. So now this is the relationship between alpha, I'm sorry, relationship between linear expansivity and area expansivity. So now we'll be moving to cubic expansivity. Cubic expansivity or volume expansivity. Call it volume expansivity or cubic expansivity. All right, I think I can claim this. Yeah. So cubic expansivity is simply the change in volume by unit volume by degree rise in temperature. So change in volume per degree volume per unit volume per degree rise in temperature. So now it is denoted with gamma. This is gamma here. Gamma. So this is the alphabet gamma. So this is V2 minus V1 over V1 and change in temperature. So here is my cubic responsivity or volume responsivity. So this is the formula for um cubic responsivity or volume expansivity. So here I have this. So now I can also say cubic responsivity is equal to V2 minus V1 over V1 theta. All right. So these are the two formulas for cubic expansivity or volume expansivity. So now what I want to do again is relationship between the relationship between cubic expansivity and area sorry, the relationship between cubic expansivity and volume expansivity. So I'm going to do that just like we did this one, but then I'm going to make it, since we already did something like this, I'm going to make it faster. Then we'll move to working example. All right, so don't forget, so I'm just going to do this quick. This will become gamma V1 theta is equal to V2 minus V1. So if I'm making V2 the subject of the formula, I'll have V2 equals to V1 plus gamma V1 theta. And then here I can say V1 is common, right? So this will become V1 bracket 1 plus gamma theta. All right, so this is what I have. So here, and don't forget, I also do something like this. L2 is equal to L1 1 plus alpha theta. Don't forget, volume is equal to length times breadth times height, right? So which means V1 can also be equals to L1 times V1 times H1. And then V2 can be equal to L2 times V2 times H2. So this is this L1 V1 H1. And then this is L2 V2 H2. All right, this is what I have as this. So what I'm going to do is I'm simply going to substitute just like I substituted when I was doing that of area responsivity. So here I'm going to have instead of V2 here, I'm going to have L2 V2 H2. And instead of V1, I'm going to have L1 V1 H1. So this is going to be L1 V1 H1 bracket 1 plus gamma theta. All right. So L2 V2 H2 is equal to this. So I can have L1 open bracket 1 plus alpha theta times V1 open bracket 1 plus alpha theta times H1 open bracket 1 plus alpha theta equals to L1 V1 H1 open bracket 1 plus gamma theta. All right. So what I'm going to do here is I'll multiply this by this by this, and I'll have L1 B1 H1 open bracket 1 plus alpha theta Q or alpha theta raised to power 3. Then I have L1 B1 H1 open bracket 1 plus gamma theta. So here L1 B1 H1 can cancel out this. These two are going to cancel out themselves. Then here I can open the brackets by saying 1 plus alpha theta, alpha theta, then 1 plus alpha theta, then 1 plus alpha is equal to 1 plus gamma theta. So here I'll first multiply these two, and I've multiplied these two once. When I multiplied it, I got 1 plus 2 alpha theta plus alpha square theta square, right? So I'm now going to multiply this by this. It's equal to 1 plus gamma theta. So here I'm going to multiply 1 times 1, 1 plus alpha theta plus 2 alpha theta plus alpha square theta square plus 2 alpha square theta square plus alpha square theta square plus alpha cube theta cube plus 1 plus gamma theta. All right, I already explained how I open this bracket then, but I'll just go over it again. 1 times 1, 1, 1 times alpha theta, 2 times 2 alpha theta times 1, 2 alpha theta, 2 alpha theta times alpha theta, 2 alpha square theta square times 1, alpha square theta square, and alpha square theta square times alpha theta, alpha cube, theta cube. All right, so I'm going to collect like terms. I will have 1 plus this because they are like terms. This is going to give me 3 alpha theta. These two are also like terms. This is going to give me 3 alpha square theta square. I hope what I'm writing is clear. All right. So plus alpha cube theta cube equals 1 plus alpha theta. Don't forget, I said anywhere you have alpha square and then alpha cube or alpha raised to power 4 or the power of alpha, they are very, very negligible. So I'll take these two guys as 0. So I'm going to have 1 plus 3 alpha theta plus 3 times 0 times alpha square, sorry, times theta square plus 0 times theta cube equals 1 plus gamma theta. So here, anything multiplied by 0 is 0. So these two are automatically going to become 0. And I have 1 plus 3 alpha theta is equal to 1 plus gamma theta. So here, I can subtract 1 from here or bring this one to this side. And then this is going to cancel out this. So I have gamma theta is equal to 3 alpha theta. And here, theta can cancel out theta, right? Theta cancelling out theta. And I have gamma is equal to 3 alpha. So this is the relationship between cubic expansivity and linear expansivity. Why this is the relationship between area expansivity and linear expansivity. So I have these two guys here. Now we can move to working examples. So I have these two. Like we can move to working examples real quick. So I'm just going to write this at the corner of the board at this top corner here. So we can be seeing it. All right. So the first example says a rod of length 2 meters. A rod of length 2 meters becomes 2.01 meter when taken from ice to steam. From ice to steam, what is its cubic expansivity? The first thing is when taken from ice, what is the temperature at ice point? Temperature at ice point is 0 degrees Celsius, and temperature at steam point is 100 degrees Celsius. So my theta 1 is 0 degrees Celsius. My theta 2 is 100 degrees Celsius. So it says a rod of length 2 meters, that's the actual length, which is L1, is 2 meters, becomes 2.01 meter. L2 becomes 2.01 meter when taken from ice to steam point. What is this cubic expansivity? So now I can say alpha is equal to L2 minus L1 over L1 theta. But then don't forget, they didn't ask us to find linear expansivity, they asked us to find cubic expansivity, which is this. Gamma is what they asked us to find. We don't have gamma. And then the question say a rod of length, so what we are going to do here is, firstly, we are going to find the linear expansivity. The linear expansivity also is not given. Linear expansivity is not given. Cubic expansivity is not given. So we'll find alpha first and we use alpha to get gamma. So what I'm going to do here is, this is equal to, what's my L2? L2 is 2.01 minus 2 over 2 times 100 minus 0, which is 100. So I have this. So I say alpha is equal to 0.01, all right, divided by 200. So I'm going to divide 0.01 by 200. I'm going to have this is equal to okay. So after dividing 0.01 by 2, I have my alpha to be equals to 5 times 10 raised to the power of minus 5 per Kelvin. All right. So I have this as my alpha. Don't forget the relationship between cubic expansivity and linear expansivity. So my linear expansivity is this. My gamma expansivity, my cubic expansivity, which is gamma, is going to be 3 alpha. Gamma will be equal to 3 times 5 times 10 raised to the power of minus 5, which is going to give me 15 times 10 raised to the power of minus 5 per Kelvin, or 1.5 times 10 raised to the power of minus 4 per Kelvin. So what I'm going to do is I'm going to look for the option that has this answer, that correlates with this answer, 1.4 times 10 raised to the power of minus 4. So that's option C. 1.5 times 10 raised to the power of minus 5 is option C. So we'll be moving to the next example. I hope you guys got me what I did here. I simply found my alpha, which is linear expansivity. I found the value of my linear expansivity. I evaluated it and I got this answer 5 times 10 raised to the power of minus 5. So I said the relationship between volume expansivity, which is cubic expansivity, and linear expansivity is. So I did this and I have 3 times 5 times 10 raised to the power of minus 5, and it gave me 1.5 times 10 raised to the power of minus 4. All right. So move to the second example and then we'll move to another topic. Okay, I guess time is not on our side. So after this example, just move to another topic in the next class. All right. So the question says, the linear expansivity of brass is 2 times 10 raised to the power minus 5 per Celsius. The linear expansivity of brass is 2 times 10 raised to the power minus 5 per Celsius. If the volume of a piece of brass is 15 centimeter cube at 0 degrees Celsius, the volume of brass is 15 centimeter cube, 15.00 centimeter cube at 0 degrees Celsius. Find its volume at 100 degrees Celsius. So the volume at 100 degrees Celsius is what I'm looking for. Don't forget, theta is equal to change in temperature. That's theta 2 minus theta 1, which is going to give me 100 minus 0, which is 100. So don't forget, I said volume expansivity gamma is equal to V2 minus V1 over V1 theta. So I'm going to replace everything here. Don't forget, the question says alpha, which is linear expansivity is this. So I have to find my gamma first. So gamma is what? 3 alpha. So this will become 3 times 2 times 10 raised to the power minus 5. So which means my cubic expansivity is 6 times 10 raised to the power minus 5. I think you guys are following. So I have this. So what I'm to do here is I'll just replace this into my equations here, into my formula, I mean. So I'll say 6 times 10 raised to the power minus 5 is equals to V2 is what I'm looking for, minus my V1, which is 15 centimeter divided by 15 centimeter times 100. So this is going to give me 6 times 10 to the power minus 5 is equal to V2 minus 15 divided by 1500. That's 1500. So I cross multiply. I have 6 times 10 to the power minus 5 times this is equal to V2 minus 15. All right. So here I'm going to multiply this by this. So this is going to give me, let me just do it directly. 96. 6 times this is 90. 0 times 10 to the power minus 5 is equal to V2 minus 15, which is going to become 9 times 10 to the power minus 2 equals to V2 minus 15. So I'm going to bring this to this side, and it's going to become plus. So this is the same as 0.09 is equal to V2 minus 15. So bringing this to this side, I have V2 equals to 0.09 plus 15, and I say V2 is equals to 15.09 centimeter cube. So my answer there is 15.09 centimeter cube, which is option B. So that's how we work with all of this. You calculate your answer, you interpret the questions, and then you have it. So this is my answer here, which is option B. So now we'll meet in the next class. I think you guys understand this very well. So you guys should do well to study the past questions. You can get tpaths past questions, and then you study your past questions. The exams are fast approaching, and then I wish you guys good luck. Have a nice day.